Hello everyone, our project focuses on the analysis and redesign of a countertop air fryer. For product overview, the air fryer uses rapid hot air circulation technology to cook food with little or no oil, providing a healthier alternative to deep frying. We identified two customer groups: household users who prioritize convenience and healthy cooking, and commercial users who need larger capacity and more advanced cooking features. Based on market growth trend, we selected a production volume of 50,000 units per year. For the function analysis, we performed a function analysis to break down the air fryer's main functions, which is cooking food. Key subfunctions include generating heat, circulating air, containing food, ensuring safety, providing user controls, improving aesthetics, and reducing noise. This helped us understand what functions the product must deliver. For the function component mapping matrix, we have mapped each function to the components responsible for performing it. For example, the heating element generates heat, the fan circulates air, the thermostat controls temperature, and the PCB manages user inputs and system control. This mapping helps connect customer needs to physical components. For the commonality table and the functional differential table, we have analyzed which component and function should be shared across product variants and which should be customized. Components such as housing, plug, screen, and safety features are common between both versions. However, functions related to cooking capacity, airflow, temperature control, and performance are differentiated to meet the needs of household and commercial customers. For the product family design, we have developed a modular product family. The household version uses a single heating element, fan, and a basket, while the commercial version includes dual heating elements, dual fans, dual basket, and additional controls for higher capacity. Both versions share common interfaces and structural components, which helps in reducing manufacturing complexity while allowing product customization.
To begin the design for manual assembly, we look at the quad chart and identify that the housing and the basket have plenty of opportunity for cost reduction based on their position in the quad chart. In this case, the housing is the platform and the basket is the module. We identify that there's a lot of opportunity to reduce substantial amounts of weight in the original design by reducing the cross-section thickness throughout the basket. To do this, we identified that DFA-3 can be used to prefer snap fits for the handle instead of trying to do everything as one piece, and DFA-10 can be used to add corners, in this case round corners, to make the grill easier to insert into the basket. We also mentioned in our previous video that the preferred assembly sequence has a lot of reorientation to assemble all the parts to obtain the final product. And it also requires the worker to hold parts in place while assembling everything else, which makes things quite more difficult and quite more costly. In this case, we redesigned based on DFA-12 to prefer Z-assembly and minimize turning over the part and rotating it to assemble everything. In this case, this includes the fan, the heating element, and the PCB no longer require holding down and reorienting in the housing to assemble everything in place. Also, DFA-4 makes the screws for the assembly significantly easier to get to assemble the screen and PCB and the fan, as opposed to our initial design where the screws did not have as easy hand and tool access. We also integrated the top housing with the remaining housing using DFA-1 to reduce the part count. Based on these changes, we see that the assembly time was initially at 390.82 seconds and the efficiency was at 10.75%. After all these design changes, and noting that the improvements were notably in the screen, PCB, basket, and screws, in this case we also reduced the number of screws, we took that down to an assembly time of 297 seconds and 14.14% efficiency.
So here we have the design for automated assembly chart. So you can see the different elements that we had here were the most important in our quad chart here. So the manufacturing cost and functional importance was both high for all the components that are involved in our automated assembly sequence. So the PCB, heating element, and fan. And you can see by the changes we made, just making it easier to assemble by aligning those features and applying the principles. We brought the time down from 131 down to 123. And then for the design for automated assembly, we took this whole housing and we completely gutted it and overhauled it. Originally, it was bolted all the way through, and this fan and heating element were attached to the indoor ceiling of this housing. We removed that ceiling to make this easier to manufacture, and also allowed for Z-insertion assembly by just putting bolt holes through everything and aligning it that way, making it a lot easier to facilitate orientation and also increasing parts symmetry. And we reduce fasteners because there's less wires and such in here.
For the top housing, the most critical dimensions are the PCB mounting hole locations and the housing interface dimensions, since they ensure proper assembly and alignment of internal components. A tolerance of 0.5 mm was selected because it provides sufficient accuracy for assembly while keeping manufacturing costs low. The housing is made from ABS plastic and is produced at a volume of 50,000 units per year. After comparing several manufacturing processes based on material geometry, tolerance, and production volume, injection molding was selected because it was the only process that satisfies all design requirements. After selecting the manufacturing process, we analyzed the housing design our team created previously using DfM Pro. The software identified several manufacturability issues. These included non-uniform wall thickness, insufficient draft angles, sharp internal corners, and the presence of undercuts. This slide summarizes the original housing design before any DfM improvements were made. The original design had a volume of 183 cubic inches and a mass of 6.62 pounds. Because of the larger material volume and the manufacturing issues identified by DfM Pro, the estimated material cost was 5.5 per part, including operating and tooling costs. The total cost was approximately 6.33 per housing. This design met the functional requirements, but it was not optimized for manufacturing efficiency or cost. To improve manufacturability, several DfM changes were implemented. The wall thickness was reduced and made more uniform throughout the housing. Draft angles were added to the side walls to improve mold release. Corner radii were increased to improve material flow, and undercuts were minimized. The changes reduced the volume from 183 to 117 cubic inches and reduced the mass to 4.32 pounds. As a result, the total manufacturing cost decreased from 6.33 to 3.99 per housing, and the design achieved a cost reduction of approximately 37%.
When it came to the manufacturing process selection for the basket itself, there were many possible options considering we were using aluminum as a material. This got worked out pretty quickly after considering the shape of our design being a dish sheet. This left us with sheet metal working, machining, and additive manufacturing as possible options for machining that would be able to handle the shape of our design. Working down the requirements, all three fit specifications for mass, section thickness, tolerance, and surface roughness. In the end, the economic batch size left sheet metal working as the only possible process for manufacturing our design. For our design, we applied several design for sheet metal principles to make the part easier, faster, and more reliable to manufacture. These guidelines helped us reduce unnecessary complexity, avoid manufacturing problems, and make sure the design could be produced using standard sheet metal processes. We used simple bend geometry and kept the form consistent so the part could be produced from a single flat sheet. We also minimized the number of setups and manufacturing steps. This reduces production time, lowers cost, and decreases the chance of errors during fabrication. We designed the part so most of the features can be cut in one flat pattern and then formed with a limited number of bends. We avoided unnecessary cuts, bends, or secondary operations. We avoided sharp corners because they can create stress concentrations and make the part more likely to crack or fail. Rounded corners also make the part safer to handle and easier to manufacture. Finally, we avoided sharp bends by using reasonable bend radii. This helped prevent cracking during forming and improves the strength and quality of the finished part. This slide shows our initial cost analysis before applying DfM improvements. We used aluminum 1100 sheet metal with a production volume of 50,000 parts per year. Based on the material, operating, and die costs, the total cost came out to about $12.69 per part. Most of the cost comes from the material, so this gave us a clear area to focus on when improving the design. This slide shows the design after applying our DfM improvements. We focused on making the sheet metal part easier to manufacture by ensuring the blank was developable, reducing extra setups and steps, using standard punches, and avoiding sharp corners and bends. These changes simplified the blank design and reduced the overall mass from about 10,894 grams to 7,005 grams. As a result, the material, operating, and die costs all decreased, bringing the total cost down from about $12.69 to $11.04 per part. Overall, applying these DFSM principles made the design more manufacturable and cost-effective. Here's a deeper dive into the cost comparison between the two designs. The pre-DFM design cost was about $12.69 per part, while the post-DFM design dropped to about $11.04 per part. That gave us a total cost savings of about $1.66 per part. The graph also shows how production volume affects cost. As quantity increases, the cost per part decreases because fixed costs like tooling and setup are spread across more parts. Even at higher volumes, the post-DFM design stays lower than the pre-DFM design, showing that our design improvements consistently reduced the cost and made the part more efficient to manufacture.
An enhancement to our device would be a software-based application that would be available for download on all phone platforms. This would improve the air fryer user's experience by allowing users to remotely control, monitor, and optimize both household and industrial-grade systems while reducing energy and food waste. The software would allow remote control of all air fryer systems, real-time cooking updates with built-in timer and alarm notifications, and user-friendly interface for adjusting temperature and cooking time. It would also come complete with automatic shutoff and safety alerts, and would allow for multi-unit control for commercial or industrial use. This would add a lot of convenience for a customer by allowing users to adjust cooking settings without being near the appliance, which in turn prevents overcooking through timed alerts and notifications. The app would also reduce safety risks by including automatic shutoff and remote power control. Additionally, it would give commercial users the ability to control and synchronize multiple air fryers, saving a lot of time for industrial uses. This would also help improve cooking consistency across multiple batches or machines. Environmentally, it would reduce unnecessary electricity use through remote shutoff and smart timer controls, lower food waste by helping prevent overcooking or burning, and support more sustainable cooking habits for both household and industrial users. In conclusion, we were able to achieve our goals of reducing parts to reduce costs, redesigning for better ease of assembly, and manufacturing our parts at a lower cost. We were able to reduce manual assembly by 93 seconds and lowered our automated assembly cost by $8.55. We were able to significantly reduce the cost of our plastic housing by improving the geometry, and we were also able to reduce the cost of our basket by reducing the weight and modifying the manufacturing processes.